Okay, why don't we get started? My name is Will Robertson, and I'll be your session chair for the second of the system security sessions here at USENIX Security. We have three very nice papers for you today, so I hope everyone is ready to pay attention after a very nice lunch. Just one note before we get started: if you have questions during the Q&A sessions, please come up to the microphone and announce your name and affiliation, if you would, for the recording. Otherwise, let's get started. So first up, we have BootStomp on the security of bootloaders in mobile devices by Nilo, Redini, et al. At UCSB. So please take it away.
Thank you very much for the introduction. My name is Nilo, and today I'm going to present to you BootStomp on the security of bootloaders in mobile devices. This work has been done by me and by several other colleagues at UCSB Santa Barbara. So let's start. What is a bootloader? A bootloader is a software module which initializes the device and its peripherals, loads the kernel from a secondary storage, and jumps into it. In this work, we focused on Android bootloaders. So, how do they look? In Android bootloaders, there is no standard. For example, ARM just gives some guidelines, but the manufacturers can do basically whatever they want. The booting process goes through several different stages, and it protects the integrity of users' devices and data through a mechanism that is called trusted boot. Also, these bootloaders offer a mechanism which is called the bootloader unlocking, and a user can use this in order to unlock the bootloader and load a custom OS. So why attacking bootloaders? What's the point? Well, if an attacker controls the bootloaders, he might boot a custom Android OS and install a persistent rootkit. He could brick the device, and in some cases, as we will see, he can achieve controls over peripherals. There are 4 properties that a bootloader should always hold. First of all, the Android OS is verifiably to be in a non-tempered state. Second, a root process cannot interfere with the peripheral setup. Third, a root process cannot unlock the bootloader. And last, a physical attacker cannot unlock the bootloader. So let's see the threat model that we use in this work. In this work, we assume that an attacker has control over the Android OS, which basically means that she has root privileges. So one may ask, OK, cool, but if an attacker has root privileges, it's game over. Why even bother? Well, the safety properties that I mentioned right before that should always hold, no matter how powerful is the attacker. Here's an outline. As first, I'm going to tell you guys the booting process, then the bootloader unlocking mechanism. Then I'm going to introduce BootStomp, our tool. Then we'll see the evaluation, the mitigation, and at the end, the conclusions. Let's start with the booting process. So ARM defines up to 4 different exception levels. An exception level basically is a mode in which the processor operates. For this presentation, we care only just about 3 mainly. EL3, which basically is the God mode, in which the processor has full visibility of all the memory and all the registers. EL1, which basically is the kernel mode. EL0, which basically is the user mode. The first stage of the booting process involves up to 3 different bootloaders. BL1, which is a very small bootloader, which is in the ROM of the device, whose purpose is basically to locate, verify, and execute a second bootloader, BL2. BL2, in turn, is going to locate, verify, and load BL31. And these last 2 together are going to set up the 2 different words, the secure word and the non-secure word. Now, the secure word is usually referred as TE, Trusting Execution Environment, and in ARM is called Trust Zone. Just to give an example, for example, in God mode with EL3, the processor has full visibility of also the memory which is mapped for the secure word. He has control over everything. In kernel mode, in non-secure word, for example, the OS cannot access directly the secure word. BL31, the last of the 3 bootloaders, first is going to locate, verify, and load the trusted OS, which in turn is going to set up all the peripherals. And after that, it's going to locate, verify, and load a further bootloader called BL33 in the picture, which is going to locate, verify, and finally load the Android kernel. Now, throughout this presentation, I'm going to refer as bootloader, the very last bootloader, BL33 in the picture, and with the term Android OS, the Android kernel. As you can see from this simple explanation, there is literally a chain of verifications which goes through BL1 to the Android kernel, and this chain is called chain of trust. This chain of trust is actually used in order to avoid persistent rootkits. This chain of trust can be broken at the very last step with the unlocking mechanism, which means that if a user wants, can unlock the bootloader, and the bootloader will not try to verify the Android kernel before actually loading it. OK, let's talk briefly about the unlocking. The unlocking procedure takes 2 steps. First of all, the user has to unlock the screen, go into the Android option, and set the OEM unlocking. After that, she has to restart the device and enter in what Google called the fast boot mode. In this mode, she can send a few commands, and the bootloader is unlocked. This 2-step procedure is thought to protect the device from 2 different attacks. First of all, the first step is thought to protect the unlocking mechanism against an attacker who has control over the physical control over the device, because the idea behind is that the attacker cannot know the unlocking phrase to unlock the screen. And the second is thought to be against a root process which might run on the phone, because a root process cannot just reboot the device, enter in the fast boot mode. The unlocking state, which is called device security state, which basically means the bootloader is locked or unlocked, is saved on persistent storage. This information should only be writable only by high privileged components, for example, the bootloader itself or SecureOS. So the question that we asked ourselves was, can a compromised Android OS affect the booting process? Well, what we found out is that, yes, it can. Let's give an example. As I said before, the bootloader has to read from the persistent storage in order to find the Android OS, and eventually loads it. Now, let's assume that the Android OS is compromised. What it can do is that it can write some information on the persistent storage, which will get affected as well. And after the reboot of the phone, the bootloader will read this information, and it might be tricked in some behavior that it wasn't intended to. So in order to find this type of vulnerabilities and to verify the safety properties that I mentioned before, we had to design a new tool. Now, bootloaders are usually hard to analyze. Why? The source code is hardly available. What we usually deal with are binaries. And most of the time, these are blobs, which means that the file format is not known and sometimes is proprietary. Second of all, dynamic execution is impractical. Why? Because the hardware is required. The bootloaders work with hardware, and without the hardware, you cannot get the information that they will get during the booting process. Third of all, they execute before the Android OS, which means that we can't really rely on known libraries or syscall. There is no such a thing as man copy. Usually, the developers, they write their own functions that they are going to use. OK, let's call about the tool BootStomp. BootStomp is an automatic static binary tool for finding security vulnerabilities in bootloaders. The goal here is to determine whether an attacker controlled data can influence the bootloader intended behavior. Also, what we wanted was a traceable output, which means that when the BootStomp produces an output, the analyst has to be able to read the output and understand if the bug that we are saying is indeed a bug. BootStomp uses multi-tag taint analysis based on under-constraint dynamic symbolic execution, which means that it uses a fully symbolic taint analysis engine to trace attacker-controlled data. So as being a taint analysis engine, 4 things must be defined. Sorry, no, OK. BootStomp looks for 4 different types of vulnerabilities. Arbitrary memory writes, arbitrary memory reads, loops that the attacker can control the number of iterations, and the bypass to the unlocking mechanism. Basically, what BootStomp does is looking for functions which override the security state on the persistent storage. This is an overview of the system. We start from the binary blob, from the bootloader. BootStomp takes as input the bootloader, and this goes to a first module which is built on top of X-rays, which basically automatically identify a set of seeds and a set of sinks, takes them and send them to a second module which is built on top of Anger, which carry on the analysis and eventually produce the alerts for the analyst. Okay, as I was saying before, as being a taint analysis engine, there are 4 things that we must define. What we mean when we're scenes of taint, taint propagation and removal, sinks of taint, and taint checking. Let's start from the seeds of taint. We consider seeds of taint any data which is read from persistent storage, and also the data which is used by the unlocking procedure. Now, in order for the bootloader to have this data must be read from the hard drive, right? So BootStomp must find the functions that are actually read from the hard drive. How does it do that? Well, we actually found out that in bootloaders, log strings are very common. So what BootStomp does is that it looks for some known keywords. For example, in the picture you can see EMMC and read. When it does a usedef analysis, and it understands which functions actually would trigger the log string. In this case, the first function in the picture. Once you found the function, it carries on a further analysis, which is a type inference analysis, in order to understand which parameters should be tainted. And this depends on the function. For example, in this case, BootStomp would understand that the function is a function reading from the hard drive, from the disk, and it looks for a buffer to taint, right? Because eventually it's going to be a buffer containing the data read from the hard drive. So, for example, if it understands that a parameter it's a string, it won't taint it. If the type of an argument cannot be inferred, it would taint it. Optionally, the seeds of taint can be provided by a security analyst. This is useful for finding the locking function, because we noticed that several of them do not contain log messages, which is not true for the other functions which read from the hard drive, which reads from the hard drive. Okay, taint propagation and removal. Taints are symbolic expressions which encode how the value is computed. The taint is propagated and removed implicitly during the dynamic symbolic execution traversal. So to give an example, let's assume that we have this code, right? The first instruction is a function call to a function called the seed func. This func will return a value which get assigned to a variable called ty. This, in a symbolic word, means that the symbolic variable ty takes a freshly created symbolic variable called taint ty. Let's assume that after that, another variable x takes the value ty plus 5. This, in a symbolic word, means that merely the variable x takes taint ty plus 5. So as you can see from this simple example, the variable x encodes how the tainted has been propagated from the very beginning up to their assignment. And this is how taint propagation works. On the other hand, if x at some point takes some hard-coded value, in a symbolic word, it's going to happen the same. And this is how the taint is removed. OK, let's talk about sinks of taint. We consider a sinks of taint memcopy-like functions, which means that, the approach here is the following. We thought that if the attacker has control over the destination buffer and or the source buffer, it could have arbitrary read and or write, right? So one sink of taint that we define is our memcopy-like functions. How do we find them automatically? Well, BootStomp looks for small functions in terms of number of basic blocks that contains loop copying data from one buffer to another. Also, by looking at bootloaders, we saw that this type of functions are called many times throughout the code of the bootloaders. Therefore, as a further heuristics, BootStomp understands how many callers this function have And we use a threshold in order to say, OK, this is a memcopy-like function. Another thing of taint is the reference of a tainted variable, a comparison of tainted variables in loop conditions. The idea behind this is that if a loop condition is guarded by, let's say, 2 tainted variables, an attacker could control the number of iterations that the loop is taking, causing, for example, a denial of service. And finally, a right to a persistent storage of a tainted variable. Taint checking. An alert is raised when a tainted variable reaches a memcopy-like function, gets dereferenced, can control the number of iterations of a loop, and finally gets written to persistent storage. Also, a traceable output is produced, which means that together with the alert, we provide the address of every basic block, which goes from the seed of taint up to the sink of taint. Let's talk about limitation. Of course, as BootStomp relies on dynamic symbolic execution, it suffers from the path explosion problem. So one thing that we did was to limit the number of function traversal, which means that BootStomp every time finds a function call, it checks if any of its argument is tainted, and if so, if the number of functions which are being followed up to the point is within a threshold. If so, it steps into the function. Otherwise, it steps over. We also limited the number of times we analyze the loop. We use a threshold for this. And finally, we set a timeout, which, if I remember correctly, is set to 15 minutes on the actual tool. Let's talk about the evaluation. BootStomp has been evaluated against 4 different bootloaders. They are LK from Qualcomm, NVIDIA bootloader, Huawei, and MediaTek. Of LK, we used 2 different versions. The latest one that we could find, and an old one which we knew was containing bugs. Out of 36 alerts, we found 7 bugs, and six of them were 0 days. OK, good, but one may ask, how bad are them, right? Well, it turned out that they are pretty bad. In this picture, you can see that we gain arbitrary code execution on the bootloader. OK, but what can you do with it? Well, a lot. For example, we saw that some bootloaders, if you remember the first picture that I showed to you, run with EL3, which means that if you have code execution on that bootloader, you have control over the entire device. We also ran an evaluation for seeing how good was BootStomp to find a locking bypass. And we got 3 warnings, 2 for Qualcomm and 1 for Huawei. Now, these results don't mean that they're actually exploitable. It means that the locking procedure of these devices at some point is going to write on the hard drive. Here is an example of a bypass bug. So in this example, first, an expected digest is retrieved from the hard drive. Secondly, an ON key, which is known only by, which is secret, is known only by the device owner, is used to compute another digest, and these 2 digests are checked. If they are different, the procedure exits. If they are the same, an hard-coded string is hashed using the key digest. Eventually, the final digest is written on the hard drive. Now, even though an attacker cannot know the ON key, what he can do is that he can read the expected digest from the hard drive. He can compute the last hash function using the hard-coded string and can write back the result on the hard drive. From that point, the bootloader is going to be unlocked. OK, let's show some mitigations. So a mitigation to the bootloader bypass that Google uses is that the key used to encrypt and decrypt the user data contains the security state, which means locked or unlocked. If the state changes by any reason, the key changes, which means that the user data cannot be read anymore, and the user has to factory reset the phone. The solution that we proposed was that the security state could be stored in the eMMC replay protected memory block, and one can modify slightly the trusted OS to allow only the bootloader to modify it. And which means that when the OS is loaded, this partition can be write protected. So the OS cannot write on the partition in any way. Conclusions. All the bugs that we found were reported, acknowledged, and have been already fixed. And this, to the best of our knowledge, was the first study to explore Android bootloaders. We proposed a completely automatic technique to analyze bootloaders. We also found 60 days in various bootloaders, and we already open sourced the tool. I will get any questions.
Let's thank the speaker. So we have some time for questions. If you have one, please approach the microphone. Okay, I have a question. So very interesting work. It seems that you found quite a few bugs for Android, and I was just wondering, did you think about the generality of this approach? Like, how easy would it be to apply this to, say, iOS or Chrome OS or some other platform?
So it could definitely be applied. I only think that it could also be applied to other bootloaders. We haven't done it yet, but we are planning to do it.
Marco Jean, Hamburg University of Technology. Have you tried your tool to work on the open source untrusted firmware?
Open source as if no, we didn't try.
Okay.
We haven't tried.
Might be a
good
case.
Might be interesting actually. Yeah. Thanks.
Okay, so one more question. You showed some exploits or some evidence of exploitability for some of these bugs, but how far did you really go with this? So I understand that many of these were...
This, I think that was exactly the... You mean this one, right?
For instance.
So this, in conjunction with another bug that we found on the bootloader, allowed us to have this.
But was that the only kind of full POC or direct in the direction of a POC that you did, or did you do this for all of the bugs that you considered true positives?
Oh no, okay. So all the bugs that we found were exploitable, but we ran this far only for this one, just to see if we could actually do it.
Okay.
Let's talk. So if I understand correctly, in your symbolic execution,
yes,
it's like static analysis, and you will encounter some path explosion problem. So my question is, do you maintain a value domain when you do a symbolic execution?
Sorry, can you repeat?
Do you maintain a value domain when you do a symbolic execution?
A value domain?
Yes.
No, not really.
How do you solve the memory alias problem?
Oh, okay. So, for example, if the bootloader has some address that we know, okay, we look for if he has the BSS section, for example, the global section. In the case, if he has, we unconstrained every possible byte.
Okay. So it's like essentially when your taint goes to the memory, and you assume the whole memory is tainted.
No. In the case we just unconstrain the memory, we won't taint it. We taint only what is being read from the hard drive. We unconstrain the memory just because we don't want to make assumption what the memory could contain.
Okay. But statically, you do not have the concrete address of the memory.
Sorry?
But in static analysis, you do not have the concrete address of the memory.
Yeah, exactly. But if we know where is the BSS, because it's written on the header, we know the addresses, right? We know the size.
Yeah.
So we just unconstrain everything.
Yeah, that's for global memory. That's for global
data.
For
global.
But what about like stack?
For the stack?
Yeah.
Oh no, okay. In the case in which we cannot know the address, we just leave it unconstrained. If the analysis cannot go further, we give up.
Okay.
Yeah.
Okay, I got it. Thank you.
Okay, if there aren't any more questions, let's thank the speaker again.